Okay, so this is the Virtual Residency Workshop 2023, Tuesday, June 27th. And I'm just finishing out. So think of this as part 2 of components and design of an HPC cluster. This is Henry again, and let's dive right in from where we left off in part 1. So the facility. So what are the considerations you have to think through with respect to where you're going to put the HPC cluster, or where your institution chooses to put the HPC cluster? Space, power, cooling, network, and then a whole bunch of other stuff. So for space, the big question is, how many rack units are you consuming? A rack unit is 2 feet wide by 1 3/4 inches high. Depth varies anywhere from 3 to 4 feet. Usually, I've seen 42 inches or thereabouts is fairly normal, but somewhere in that range. A typical compute node will fit in 1 rack unit, or 1U. A typical large RAM node might be a 1U or a 2U. A typical GPU node could be anything from, you can in principle have, for lower powered GPUs, you can have a 1U GPU node. They can go all the way up to several U. I've seen 5 and 6U GPU nodes that have several GPUs in them. Power, how much do you need? In the olden days, like 15 years ago, an individual compute node might draw a couple hundred watts. By 2015, we were in the 350 to 450 watt range. Now, a typical compute node is going to run 500 to 700 watts, depending what's in it. And a GPU node. So if you buy an 8-way GPU box, you could easily be looking at 5 to 10 kilowatts, 5 to 10,000 watts of power for a single box. And that is only going to get worse. Recently, one of my colleagues pointed me to an article that said that it was likely that within 5 to 10 years, an individual CPU chip would draw 1 to 2 kilowatts, 1 to 2,000 watts per chip, not per node. So a node would be as much as 5 kilowatts with no accelerators, no GPUs or anything. Just a regular compute node could be on the order of 5 kilowatts. That is a terrifying prospect, to be perfectly honest. I don't know how we will deliver that volume of power and cooling per rack. I think what we'll end up doing is just using like the bottom few units of a rack, and then the rest of the rack will be blanking panels to keep the cold air trapped. And if you're designing a cluster, you need to work with the manufacturer to find out, for each configuration of node, switch, and storage, what kind of power draw do they each have? And that can be a very complicated question. I have learned way too much about how power in particular is delivered and how it works. I am not an electrical engineer. I am not a mechanical engineer. I have no business getting involved in the mechanicals of data centers, but things have gotten so crazy now, there's no choice anymore. So now I know the formula for calculating how much power a power system can deliver to an individual rack. I did not have any aspiration to know that. Now I have no choice. Oh, is it regular ice? I thought it was dry ice. Okay, well, in any case, we'll fight it out later. How's that? And a ton of cooling is just 3.5 kilowatts. A typical mid-scale institutional cluster supercomputer, where you're talking about hundreds of compute nodes, is probably going to be measured in hundreds of kilowatts. And a large-scale supercomputer is going to be measured in megawatts. In fact, the biggest, fastest supercomputer in the world today, which is Frontier at, is that Oak Ridge National Lab, I think? Frontier, I believe, draws 21 megawatts. To give you the flavor of that, that's all of the city I'm in right now, Norman, Oklahoma. It's a suburb of a mid-sized city, Oklahoma City. It's about 100,000 people. 100,000 people is about 20 megawatts. So the fastest supercomputer in the world is equal to the town I'm sitting in right now in terms of power draw. Network, how much connectivity do you need out to the world? Do you just need a few gigabytes? Do you need tens of gigabytes? Do you need hundreds of bits, tens of gigabits per second, hundreds of gigabits per second? How much redundancy do you need? Do you need multiple different paths? What happens if you have a power outage? What happens if you have a network outage? There's all kinds of things that you have to take into account depending on the scale, the budget, and the criticality of research computing to your institution. Way back in 2007, Oklahoma suffered its worst ice storm in recorded history. And much of Norman was out of power during that time, and we were running on generator. And the difficulty with an ice storm is the one thing you don't want to do during an ice storm is drive a tanker truck full of fuel. That is brutal. It's a very foolish thing to do. And so we were down to the last few sips of diesel fuel in the 2,500 gallon tank under the parking lot when the tanker truck was finally able to get through and deliver us more fuel, more diesel fuel for our generator to keep our supercomputer going. But there's lots of other considerations, right? Space power cooling network, those are the big ones. But then there's fire suppression. There's the weight limit, and that's typically measured per tile. So you may have seen in your data center or other data centers that you have these 2 foot by 2 foot tiles that have holes in them to let the cool air come through. And those are typically what are called pedestal floor, where it's a raised floor and the concrete floor is anywhere from 6 inches to several feet below the floor that you're putting the machines on, the pedestal floor tiles. And then the pedestal floor tiles are held up by basically these metal, I don't know, call them girders or whatever. They're typically not that thick, but, and then there's typically a weight limit associated with those pedestal tiles. I think we are something like 2,000 pounds per square foot on the pedestal flooring we have. I think that's the number. And you have to take that into account. You have to look at what's in the nodes in your racks and how many nodes are there. Are you going to exceed the weight limit, the weight tolerance that those floor tiles have? Are your hallways and doorways wide enough and tall enough to pass the racks through? Or are you going to have to pull all the nodes out of the racks, wheel the rack in empty, carry the nodes in by hand, and stick them back in the racks? That takes a lot longer, but more than that, you have to bring in people whose job it is to lift heavy things because you don't want your team throwing their back out lifting heavy things. What about the loading dock? Is it raised loading dock at truck bed height, or is it a ground level loading dock that would require a lift gate on the back of the truck that's delivering the equipment? This seems like a really strange question, but we had this exact problem in 2015 where we made an agreement with the vendor that they would deliver the racks always in trucks that had lift gates. And of course, about half of the trucks showed up without lift gates. And so we had to send those trucks to the other side of town to a building, a receiving center that did have the truck bed level loading dock. And then the vendor had to send a separate truck the next day that had a lift gate to carry it from one receiving place to our data center. So these things are a big deal. If it's not on the ground floor, is the elevator big enough to fit the equipment in? We had to hang some equipment off the bottom of an elevator back in 2002. This was not something I had planned to do with my life. It was sort of spectacular in an uncomfortable way, but not what I had planned. We also had a component of the cooling system in that building. We're not in that building anymore, but in that building, there was a component of the cooling system that had to go up on the roof, which was the 15th story. It had to be brought in by helicopter because the interior of the building not only didn't have an appropriate elevator, but the staircase was a winding staircase on the sort of inside of the outer shell of the building. So you need an uninterruptible power supply. You need a generator. How mission critical is this stuff to what you're doing? Are you sharing a data center with enterprise, which is going to have these things, right? I presume there's some discussion about facility considerations vis-a-vis global climate change. Any sense or consensus on how HPC facilities may change in the near term, given prevailing ideas about the climate? I am not aware of major changes. Some buildings do get designated, for example, LEED certified green buildings. And in fact, our data center has gotten some LEED certification. And I think that's becoming more common. The reality is these beasts consume so much power, require so much cooling, which, as was mentioned in the chat, cooling consumes a third as much power as the power that the cooling is cooling. So you whatever power you need, you then have to calculate an extra third of the power to cool the power. This is not a trivially solvable problem. The biggest machine, again, the biggest, fastest supercomputer in the world today consumes the equivalent power and presumably air conditioning of a suburb of 100,000 plus souls, right? There is no way you're going to make that climate friendly. You can make it less bad. You can't make it not bad. Liquid cooling can have some impact, I agree. It's a trade-off with liquid cooling because you have to pay to install the liquid cooling, but then on the other hand, the ongoing operating cost may be less because you might be reducing the amount of power draw that you need to cool your system, right? So all of these factors can play into this, I agree, but it is not trivial to run a data center without drawing an enormous amount of power. That is not, it is a reducible problem. It is not a problem you can eliminate, right? So, to the comment about locating in West Texas or Sweden, so the Texas Advanced Computing Center in Austin, at the University of Texas there, they have some innovative solutions for cooling. There are a number of locations that have made strides and have improved, and you can improve. Those improvements typically do come at a cost, but you can make improvements. I don't think you can solve the problem. If you're going to draw 20 some megawatts for a single machine, you're going to create a problem no matter what you do. The best you can hope to do is reduce that problem. Okay, now, why do we even have cluster supercomputers? You know, in the olden days, we had what were called big iron machines, and these were boutique hardware running boutique software, and they were very expensive, but you could still make a living designing, building, and selling these big iron machines. Those days, as far as I can tell, are at an end. And the reason why really comes down in the end to Moore's law. So probably most of us have some familiarity with Moore's law, but Gordon Moore, back in the mid 60s, he was an engineer at a company called Fairchild Semiconductor. And he noticed that the number of transistors they could squeeze onto a chip of the same size was doubling about, initially it was doubling about every year. Then it quickly the pattern became every 2 years. And it turns out that the capacity and the speed of a computer or its storage is roughly proportional to the transistor density, the number of transistors per unit area. So he wrote up a little paper where he described this. It became known as Moore's Law. It's really an observation, but it's held true for umpty-ump zillion years. Here's a picture of that. And this straight line, this sort of pinkish fuchsia straight line down here, and by the way, notice it's logarithmic in the vertical. This pinkish line here, this is Moore's Law. So individual computers getting it faster and faster. And up here is the fastest supercomputer in the world, measured about every 6 months, twice a year, every June and every November. And the fastest supercomputer in the world, you notice, has been getting faster and faster, faster than computers have been getting faster and faster. In fact, that's generally true of supercomputers, not just the fastest one in the world, but supercomputers in general have been getting faster and faster, faster than computers have been getting faster and faster. Why is that? Well, the individual computers are contributing to this straight line here. But what we've gotten better and better at over the years is parallelism. We've gotten better and better at jamming more cores per chip, jamming more nodes per supercomputer. So way back in June of '93, when the very first top 500 list came out, and you can visit those lists at top500.org, these are the 500 fastest supercomputers in the world by a specific measure. It was 1,000 cores and about 60 billion calculations per second. The one that came out earlier this month, just a few weeks ago, was 8.7 million cores. So 8,700 times as many cores as 30 years ago. And runs, it's a little over let me see if I get this right, quintillion calculations per second, an exaflop. The speed of the thing is 20 million times faster than the fastest supercomputer 30 years ago. And that's on 8,700 times more cores. And therefore, whatever 20 million divided by 8,700 is, I guess that's probably around 30,000 times faster per core. And here's that thing, like I was saying, 21 megawatts to power the thing. That's all of my town. So today, a top-of-the-line supercomputer will consume as much power as a suburb. Now, Moore's Law, this was an uncanny prediction. Nobody has ever made a prediction more accurate than this in the world of science that I'm aware of. In 1971, the very first x86 chip, long before they thought of calling it x86, the Intel 4004, is a 4-bit chip, itty-bitty thing, 2,300 transistors. By 30 years later, actually 38 and a third years later, Intel had a chip called Becton, Nehalem Becton specifically, that had 2.3 billion, 1 million times as many transistors as the 4004. So that was a factor of 1 million improvement over 38 and a third years, right? So that's a doubling of about every 23 months. He had said 24. Moore had said 24. Now, has this continued to the present day? Yeah, it absolutely has. If you compare the Nehalem, the top-of-the-line Nehalem from 2009 to the top-of-the-line Ice Lake in 2021, the doubling period for the speed of it has been 24 months. If you look at memory bandwidth, on the other hand, you look at what the memory bandwidth was on the Nehalem back in 2009, 36 gigabytes per second, compared to a Genoa today at 766 gigabytes per second. That's doubling every 35 months. Okay, so here's kind of a picture of Moore's Law. And to squeeze it all in, I kind of had to kind of jam everything in various places. So it's kind of going clockwise, going clockwise in a circle here. But in 1997, ASCII Red at Sandia National Lab was the very first teraflop supercomputer, 1 trillion floating point operations per second. double precision floating point operations per second. 5 years later, OU had that. 5 years later, it took up a row. It was somewhere around 10 racks, I think. By 10 years after that, you could get it as an accelerator card, a GPU or similar, right? And all of AMD, NVIDIA, and Intel, they all had teraflop cards. By 2017, 5 years after that, you could get a single CPU chip that could do 1 trillion calculations a second. And by now, and I guess this would be the Genoa chip, because it says AMD EPYC, that's 8 cores, is 1 trillion calculations a second. So we went from a room, and by the way, that was several $100 million, to 8 cores in 25 years. Multi-core, we all have heard about multi-core. You have multiple independent brains inside a CPU chip, right? They can run separate programs, or they can work together running one program, but doing different parts of the work, or doing the same work on different data at the same time. And all of the cores within that chip are using one connection to the memory, and they share the bandwidth between the memory, the RAM, and the CPU. So here's kind of a history of that. I tried to do Intel and AMD in more or less their official colors. Not perfect, but close enough. And you can see, in 1971 was the first single core x86 chip. They didn't bother to call it single core because there's no such thing as multi-core. The first multi-core chip was 2005 at Intel, and then about 6 months later at AMD. And then they kept growing and growing and growing and growing. And just this month, AMD has released a 128 core CPU chip in the Genoa line. They had released the Genoa 96 core chip back in November. Now they're at 128 cores. Intel is at 64 cores, but note that Intel has full-blown AVX 512, where they can do 32 double precision floating point operations per clock cycle per core per second. Whereas AMD, they can interpret, those chips can interpret the AVX 512 instructions, but they take twice as long to do them. They take 2 clock cycles instead of 1 for those calculations. Anyway, not getting too bogged down in that, but you can see the pattern. How does a server run? What does it cost to run a server with 128 cores? I'm going to go out on a limb and say mid to high 5 figures for a dual chip server of 128 cores, somewhere in that neighborhood. Maybe it's low to mid. I haven't run the numbers for that particular model. Also, if you're going to have that many cores, you're probably going to spring for a decent amount of RAM, and that's going to cost an arm and a leg. Why do we have multi-core? Well, in the distant mists of time, in the long, long ago, in the before times, in the golden age, the way, and by this I mean before Christmas of 2005, give or take, the way that you would speed up a CPU was you'd increase its clock speed. So that there's a little tiny crystal inside the CPU that vibrates at a fixed frequency. And every calculation, every type of instruction takes typically a fixed or a range of how many clock cycles, how many ticks of that clock it takes to do that calculation. Well, it used to be, up until late 2005, the way that you would get more speed is you would speed up the clock ticks. So I remember when you'd be excited to buy 100 megahertz, so a 0.1 gigahertz CPU chip. Then came gigahertz, then came multiple gigahertz, but that didn't keep going. And the reason it didn't keep going is the power density, the watts per square meter of a CPU chip, grows proportional to the square of the clock speed. So if you double the clock speed, the gigahertz, you're quadrupling the power density. So eventually you've got giant power draw and you're going to melt the chips. And in fact, there's a famous diagram that I've reproduced here. And here's the reference to where you can get that diagram. This is what was happening in the 90s and the 2000s. And here's a hot plate. This is how hot a hot plate. So maybe on the order of a hair dryer. And you may have noticed this if you put your laptop on your lap, especially if you're wearing shorts, right? That the thing runs pretty hot, but you're not going to die. But if we'd kept going the way we were going to get, if we kept doubling the clock speed, we were going to get to the heat of a nuclear reactor, followed by a rocket nozzle. And now this is 8 years ago, we would have been at the heat of the sun. Obviously, that's not practical. So instead, what we did was we went multi-core. By going multi-core, we could keep the clock speed roughly fixed while still increasing the number of calculations per clock cycle per chip by increasing the number of cores. Now, we have increased the number of calculations per clock cycle per core as well, but not nearly as fast as Moore's law. So by doing both that and increasing the core count, we've kept up with Moore's law. All right, why do we have clusters? Well, as I said, in the olden days, we had big iron, and big iron was great. Big iron was lovely. These were specially designed machines. They were special purpose boutique machines that were designed to do specifically high performance computing. They were big, they were fast, they were expensive, but they weren't ridiculously expensive. They were merely expensive, right? And the reason you could do that and you could have these boutique chips is because back then designing a chip and building the factory was relatively affordable. Those days are over. Today, to build a chip factory, that's at least $5 billion. There was recently an article in one of the trade journals that pointed out, I think it was Intel, I won't swear it was Intel, but one of the chip manufacturers was building a plant in the US. The initial outlay was going to be about $2.5 million. Over a 10-year period, they were going to build $30 billion worth of factory. $30 billion worth of factory. If you build a $30 billion factory and you manufacture 1,000 chips, just to break even, you've got to you've got to charge $3 million per chip. If you can sell 1 million chips, you only have to charge, $30 million per chip. You only have to charge $30,000 a chip. If you can sell 1 billion chips, you only have to charge $30 a chip to break even. So it's all about large numbers. You can't sell a boutique chip anymore because there's no practical way to break even on the fixed cost of building the factory, right? So there's that old joke about if you want to make a small fortune in supercomputing, start with a large fortune. So the way to make supercomputing profitable is to make it just one more application of essentially the same hardware, right? And the great thing is it's easy to build a cluster supercomputer out of commodity off-the-shelf components. Big iron, you typically can't do that. So in the end, big iron couldn't compete financially. Even if technologically it was superior, financially you couldn't make the trade-off work. Okay, supercomputing works best with a lot of parallelism. It's cheaper to buy a zillion cheap things than a few expensive things. So supercomputing is now, I don't want to say 100% cluster supercomputers, but near enough to. Okay. There's another problem too, which is, well, why can't we have boutique chips? Well, in the olden days, you kind of could. Now, the problem is you've got to be able to port all the codes to be able to run on your chips. And that should be trivial, right? It should be the case that the research application software, which is written in standard high-level languages, should trivially port to any platform. Should be, but ain't. That's just not how it is in practice. And the labor cost, so I mentioned here at my institution, we support over 600 research application software packages. We can't do that porting. We've got to be confident that we can trivially deploy the code on our machine. Pretty much every code has been ported to x86. There is no other CPU family that comes even close. Well, there's some that come close, but not many. People have talked about, well, can't we build supercomputers out of ARM chips? We absolutely can. But then someone has to take responsibility for porting the code. And they will. I'm very confident that that will happen. But I'm not volunteering to do it. And I'm not volunteering our team's time to do it. And I don't see our researchers volunteering to do it. So someone else is going to have to do it. Okay. I'm already way past the time that I would have had. Anyway, are there any questions about the material we've just covered? And I'll leave it there. Okay, then let me stop the recording.